Imagine staring up at the night sky, tracing the faint, glowing band of the Milky Way, our cosmic home. It's easy to forget that within those swirling stars and vast stretches of darkness lie secrets so strange, they challenge everything we think we know about the universe. Tonight, we're not just gazing at the familiar twinkle of distant suns. We're diving into the shadows, uncovering 30 of the most bizarre, mind-bending objects hidden right here in our own galaxy. Objects so peculiar they seem ripped straight from the pages of science fiction. Think about this for a moment. The Milky Way isn't just a collection of stars and planets. It's a graveyard of cosmic oddities, a treasure trove of mysteries waiting to be unraveled. Some of these objects scream across space with bursts of energy we can't yet explain. Others lurk silently, invisible to our eyes, yet bending the very fabric of reality around them. And then there are those that defy categorization entirely, things so outlandish, astronomers still argue over what they could possibly be. What if I told you some of these enigmas are closer than we ever imagined, hiding in plain sight? This isn't just a tour of the unknown. It's an invitation to step into the shoes of those who stare into the void and dare to ask, what is that? From ghostly radio whispers to celestial bodies that shouldn't exist, each of these 30 wonders tells a story, one that stretches the limits of science and ignites our imagination. So buckle up. We're about to journey through the strangest corners of the Milky Way, where the rules of physics bend and the universe reveals its most guarded secrets. Are you ready to meet the impossible? Deep in the direction of the constellations Hydra and Centaurus, something unseen tugs at our entire galactic neighborhood with a force we can't ignore. Meet the Great Attractor, a gravitational mystery so powerful, it's dragging not just the Milky Way but thousands of other galaxies toward it at over 600 kilometers per second. Picture an invisible hand in the cosmos, pulling everything in its reach toward an uncharted point in space. But here's the catch, we can't even see what's doing the pulling. This monstrous anomaly hides behind what astronomers call the zone of avoidance, a region of the sky obscured by thick dust and stars from our own galaxy's disk. It's like trying to spot a lighthouse through a sandstorm. The very structure of the Milky Way blocks our view of the very thing trying to steer us. What makes this even stranger? The Great Attractor's gravitational pull is far stronger than anything its visible mass should account for. Even with advanced telescopes peering through the cosmic fog, we've only found scattered galaxy clusters, nowhere near enough matter to explain the sheer force at work. Some theories suggest dark matter could be playing a role, weaving an invisible web of gravity we can't detect. Others propose something even wilder, that the Great Attractor might just be the tip of an unimaginably vast cosmic structure, a supercluster of galaxies so immense it warps the fabric of space-time itself. And while we're slowly mapping the secrets behind this enigma, one thing's certain: the Great Attractor reminds us how much of the universe remains hidden in plain sight. It's a humbling thought. Even as we race toward it, the cosmos keeps its most profound mysteries just out of reach. At the heart of our Milky Way, buried in the dense star clouds of Sagittarius, lurks a cosmic monster, Sagittarius A star. This isn't just any black hole. It's a supermassive leviathan weighing in at over 4 million times the mass of our Sun, its gravitational grip so fierce that not even light can escape. For decades, it existed only in theory, a shadowy giant inferred by the frantic orbits of nearby stars whipping around some unseen, unfathomable force. Then, in 2022, humanity did the impossible. We took its picture. The Event Horizon Telescope's landmark image revealed a fiery, donut-shaped ring of light bending around the black hole's event horizon, the point of no return. But don't let the serene glow fool you. Sagittarius A star is anything but quiet. Every few years, it erupts in violent flares, bursts of X-rays and radio waves so powerful they outshine the black hole's usual glow by hundreds of times. Imagine a sleeping dragon occasionally spewing fire into the cosmos, heating surrounding gas to millions of degrees. Scientists still debate what triggers these outbursts. Could it be unlucky stars or gas clouds straying too close, torn apart in a tidal ballet of destruction? What's even wilder, this black hole might be the cosmic glue holding our galaxy together. Its gravity shapes the orbits of billions of stars, a silent puppeteer orchestrating the Milky Way's grand dance. Yet for all its power, Sagittarius A star is strangely underwhelming compared to other supermassive black holes. Some devour entire stars with gluttonous fury, while ours barely nibbles, its flares mere whispers compared to the roars of distant galactic cores. Perhaps the most chilling thought, we're spiraling toward it. Not in our lifetime, not in a million lifetimes, but over eons, the Milky Way's slow churn will inevitably pull us closer to the beast at its heart. A poetic fate, really, born from stardust only to one day return to the darkness. Rising from the Milky Way's core like twin colossal ghosts, the Fermi Bubbles stretch 25,000 light-years above and below our galaxy's disk, structures so vast they dwarf everything else in our cosmic neighborhood. Discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, these immense lobes glow with high-energy gamma radiation, painting the sky in invisible light. Imagine two giant balloons, each large enough to swallow a quarter of the galaxy, hovering silently in space. Yet despite their staggering size, they remained hidden until modern technology peeled back the curtain. What could have created such enormous, energetic structures? The leading theory points to Sagittarius A star, our galaxy's supermassive black hole, having a violent tantrum around 1.8 million years ago. Picture this, a cataclysmic outburst as the black hole devoured an entire gas cloud or perhaps a wayward star, unleashing a shockwave so powerful it punched through the galactic disk, inflating these bubbles like cosmic bellows. But here's the twist. Some researchers argue the bubbles might be the aftermath of not one, but hundreds of supernova exploding in rapid succession, a stellar fireworks show on a scale we can barely comprehend. Even stranger, the bubbles' edges are razor-sharp, as if something carved them out of the interstellar medium with surgical precision. Gas and dust don't usually behave this way in space. They tend to diffuse and spread unevenly. Yet these structures stand defiantly crisp, their boundaries challenging our understanding of how energy interacts with the galaxy's delicate ecosystem. And then there's the mystery of their faint X-ray counterpart, the so-called E-Rosetta bubbles, discovered years later. These overlapping structures suggest multiple eruptions or perhaps an ongoing process still shaping them today. The Fermi Bubbles are more than just a relic of ancient violence, they're a living laboratory. Charged particles within them spiral along magnetic fields, emitting radiation that clues us into the galaxy's hidden workings. Some scientists even speculate they could be channels for cosmic rays, those elusive high-energy particles that bombard Earth from deep space. One thing's certain, whatever birthed these giants left an indelible mark on the Milky Way, a reminder that even our home galaxy has a temper. And just maybe it's not done yet. Streaking through the void like a bullet fired from some cosmic gun, the Cannonball Pulsar defies every expectation of how a neutron star should behave. Clocked at a staggering 2.5 million miles per hour, this hypervelocity rogue doesn't just move, it escapes, tearing through interstellar space so fast it could cross the distance between Earth and the Moon in just 6 minutes. Most neutron stars spin quietly in the graveyards of their supernova births, but not this one. It's a runaway, leaving behind a 13-light-year-long trail of superheated gas, a scar etched across the cosmos like the wake of a ship plowing through unseen waters. How does something so dense, a collapsed star core, weighing more than our Sun yet compressed into a sphere the size of Manhattan, get launched with such violent force? The answer lies in its explosive origins. When a massive star dies, it doesn't always explode symmetrically. Imagine a detonation so lopsided, the recoil kicks the newborn pulsar like a shotgun blast, sending it careening into the darkness. That's likely what happened to the Cannonball, but there's another, even wilder possibility. It might have been slingshotted by a second supernova. Some models suggest this pulsar was part of a binary system, orbiting another star that later exploded, the force of that detonation ejecting it like a stone from a sling. What's truly mesmerizing is the chaos it leaves in its wake. As the Cannonball plows through the interstellar medium at nearly 1% the speed of light, it rams into surrounding gas, creating shockwaves that heat particles to millions of degrees. These collisions generate eerie X-ray glows detectable across the galaxy. Yet for all its fury, the pulsar itself spins quietly. Its beacon-like radio pulses eerily steady, a cosmic paradox of calm precision amid unimaginable speed. And here's the twist, it's not alone. Astronomers have spotted other rogue pulsars, each with its own bizarre trajectory, hinting that stellar graveyards might be far more dynamic than we thought. The Cannonball is just the most extreme example, a reminder that even in death, stars can defy expectations, becoming celestial outlaws in the vast expanse of the Milky Way. One day, it will vanish into intergalactic space, forever a wanderer, proof that sometimes the universe prefers its monsters untamed. Drifting toward the Milky Way like a ghostly iceberg in the cosmic sea, the Smith Cloud isn't just another wisp of gas, it's a heavyweight contender on a collision path with our galaxy. Stretching 11,000 light-years long and 2,500 light-years wide, this colossal hydrogen structure is hurtling toward us at nearly 300 kilometers per second, carrying enough raw star-making material to spawn 2 million suns. But what really makes astronomers scratch their heads isn't its size or speed, it's the baffling secret hidden in its chemistry. Most intergalactic gas clouds are pristine, composed almost entirely of hydrogen and helium, the universe's original building blocks. The Smith Cloud, though, is laced with heavy metals like sulfur and oxygen, elements forged in the hearts of stars and scattered by supernova. This means it didn't originate in the void between galaxies. It's a wanderer with a past, likely ripped from the Milky Way itself nearly 70 million years ago, only to boomerang back in a celestial homecoming. Radio telescopes have traced its trajectory, revealing a wake of ionized gas glowing like a cosmic breadcrumb trail, evidence of its turbulent journey through the galactic halo. But there's a wilder theory. Some researchers argue the cloud's sheer mass and metal content suggest it could be the shredded remains of a failed galaxy, a dwarf companion that ventured too close to the Milky Way and was torn apart by tidal forces. Picture a tiny island of stars unraveled into a river of gas, its identity erased but its exotic composition lingering like a fingerprint. If true, the Smith Cloud isn't just a returning exile, it's a corpse of a galactic neighbor, and its impending collision could seed new star formation in our galaxy's outskirts. The clock is ticking. In about 30 million years, the cloud will slam into the Milky Way's disk near the constellation Aquila, unleashing a fireworks show of star birth as its gas compresses under the impact. Yet for all its drama, the Smith Cloud is also a puzzle piece in a larger mystery: how galaxies like ours grow by cannibalizing smaller neighbors and even their own ejected material. It's a reminder that the cosmos doesn't just build, it recycles, turning destruction into creation in an endless, elegant dance. Tucked away in the Milky Way's halo like a cosmic bullseye, Hoag's object is the celestial equivalent of a riddle wrapped in a mystery. This bizarre ring galaxy floats in near-perfect symmetry, its golden core encircled by a dazzling blue band of young stars, a structure so flawless it looks like it was drawn with a compass. Most galaxies twist into spirals or clump into egg-shaped blobs, but Hoag's object defies the mold, presenting astronomers with a puzzle that's lingered since its discovery in 1950. What's even stranger, some studies suggest it might not be drifting alone in the void but could actually be orbiting our galaxy, a satellite hiding in plain sight. Theories about its origin read like a cosmic detective story. One leading idea proposes a galactic collision, a smaller galaxy piercing through a larger one like a bullet through smoke, its gravitational shockwave triggering star formation in a ring. But here's the catch. Hoag's object shows no signs of the violent past this scenario would require. No debris, no warped core, just eerie stillness. Another hypothesis suggests it's the result of a resonance, where gravitational forces align gas into that perfect circle over eons, like ripples frozen in a pond. Yet neither explanation fully accounts for its isolation. Most ring galaxies have neighbors tugging at them, but Hoag's object floats in unsettling solitude. Then there's the halo problem. Nestled within the Milky Way's own halo, its potential connection to our galaxy deepens the enigma. If it truly orbits us, why does it look nothing like the other satellite galaxies, which are typically misshapen dwarfs? Its sheer symmetry suggests a stability that shouldn't survive the gravitational chaos of our galaxy's pull. Some astronomers argue it's just a distant background object, its apparent location in the halo a trick of perspective. But if it is nearby, it forces us to reconsider how such pristine structures can exist so close to a disruptive giant like the Milky Way. Perhaps the most tantalizing clue lies in its core. While the outer ring blazes with newborn stars, the central bulge glows with ancient red suns, a stark contrast that hints at two distinct eras of creation. This duality challenges the textbook timeline of galactic evolution, where stars typically form in waves radiating outward. Hoag's object, though, seems to have paused its star-making for billions of years before suddenly sparking that outer ring to life. Was it asleep, then reawakened by some unseen trigger, or is it a cosmic hybrid stitched together from fragments of other galaxies? Every answer only breeds more questions, and that's what makes Hoag's object so captivating. It's a celestial outlier, a reminder that the universe still holds blueprints we haven't deciphered. Whether it's a lone artist painting outside the lines or a silent companion to our Milky Way, one thing's clear: perfection in space is never accidental. And somewhere out there, this golden enigma keeps spinning, daring us to unravel its secrets. Somewhere beyond the Milky Way's bustling starfields, in the constellation Oddities, lies a region so empty it defies logic, the Oddities void. Imagine a sphere of darkness 330 million light-years wide, containing barely 60 galaxies where there should be thousands. This isn't just a quiet pocket of space, it's a cosmic desert so vast, if you stood at its center, the naked eye wouldn't see a single star in any direction. Astronomers call it the Great Nothing, and its existence challenges our understanding of how the universe structures itself. What could carve out such a staggering void? One theory points to the violent aftermath of the Big Bang, where fluctuations in density left some regions almost entirely empty. Picture a pot of boiling water. Most bubbles cluster together, but occasionally a giant one forms in isolation. The Oddities void might be that bubble, a relic of primordial chaos frozen in time. But there's a twist. The few galaxies found here are oddly young, their stars burning blue and hot, as if the void itself delayed their birth. It's as if this emptiness isn't just passive, but actively tampered with cosmic evolution, pressing pause on star formation for billions of years. Then there's the darker possibility. Some scientists speculate that the void could be the footprint of an advanced civilization. Not little green men, but a Kardashev-type 3 empire harnessing the energy of entire galaxies, leaving behind a ghostly footprint of their consumption. While that's a fringe idea, it underscores how little we comprehend about the void's true nature. Even its edges are enigmatic, fading into the cosmic web with no clear boundary, as if the universe itself forgot to fill in this corner of the canvas. Yet the Oddities void isn't just a curiosity, it's a mirror. Its emptiness forces us to confront how much of the cosmos might be missing, hidden in gaps our telescopes can't yet penetrate. For every vibrant galaxy cluster, there could be 100 such voids, silent and invisible, rewriting the rules of existence, and perhaps the most humbling thought. One day, far in the future, our local universe might look just like this, a vast, dark sea where once there were stars. Glowing in the constellation Monoceros like a celestial stained glass window, the red rectangle nebula isn't just another dying star's farewell, it's a cosmic rebellion against nature itself. Most planetary nebulae billow into delicate spheres or intricate spirals as aging stars shed their outer layers, but this one, it forms a near-perfect rectangle, its sharp corners and vivid crimson glow looking less like an astrophysical object and more like a piece of abstract art. At its heart, a binary star system pumps out intense radiation, illuminating the surrounding gas with an eerie ruby light. Yet the real mystery isn't the color, it's the geometry. Space doesn't do right angles. Gravity and explosions tend to create curves, not corners. So how did this defiant structure come to be? The answer lies in an invisible architect, a thick disk of dust orbiting the central stars like a cosmic hula hoop. As the dying star ejects gas, this disk funnels the outflow into two opposing cones, their edges colliding to form the nebula's flat walls and distinct X-shape. Imagine squeezing a balloon between two books. The trapped air would escape in jets, creating a similar angled structure. But the red rectangle takes this phenomenon to an extreme, with dust particles aligning so precisely they polarize the light, intensifying its rich red hue. Even more bizarre, the nebula's spectrum reveals complex organic molecules called polycyclic aromatic hydrocarbons, essentially the building blocks of soot. These carbon-rich compounds shouldn't survive the star's harsh radiation, yet here they thrive, painting the nebula in shades that border on unnatural. What's truly unsettling is the nebula's impermanence. In a few thousand years, a blink in cosmic time, the central stars will heat up, evaporating the dust disk and erasing the rectangle forever. What we're witnessing is a fleeting sculpture, a momentary defiance of chaos before the universe smooths it back into the familiar. It's a reminder that even in the vast, rule-bound cosmos, anomalies persist, not as mistakes but as masterpieces. In 2011, astronomers spotted something bizarre hurtling toward the Milky Way's supermassive black hole, a 3-Earth mass dust cloud dubbed G2. Most cosmic gas clouds shred like tissue paper when they approach Sagittarius, a star's gravitational maw, but this one did the unthinkable. It survived. Swinging just 36 light hours from the black hole's event horizon in 2014, G2 stretched like taffy under extreme tidal forces, then kept right on moving, its structure mysteriously intact. The event sparked a fiery debate. Was this really just a gas cloud, or did it conceal something far stranger lurking in its depths? The leading theory suggests G2 isn't a simple dust blob at all, but the swollen atmosphere of a stealth star, a dim, ancient stellar remnant cloaked in gas. Imagine a stellar corpse, perhaps a white dwarf or neutron star, plowing through the galactic center with a shroud of debris so thick it mimics a cloud. This hidden anchor would explain G2's resilience, its compact core providing enough gravity to hold the gas together despite the black hole's pull. Infrared observations added fuel to the fire, revealing that the cloud's motion matched predictions for an object orbiting Sagittarius, a star, a behavior far more typical of a star than free-floating gas. Yet not everyone's convinced. Alternative models propose G2 could be a gas cloud after all, just one born under extraordinary circumstances. Maybe it condensed from a colliding stellar wind or was ejected during a chaotic interaction between binary stars near the black hole. These scenarios, however, struggle to explain why the cloud didn't fully disintegrate. Its eerie persistence hints at forces we might not yet understand, perhaps even exotic physics around black holes that resist textbook predictions. Here's where it gets even weirder. As G2 continued its escape, telescopes caught it heating up, glowing brighter in X-rays as if stirred by some invisible energy source. Was the black hole's gravity squeezing the cloud, igniting shockwaves within it? Or was this the signature of a hidden star's magnetic field interacting with surrounding plasma? Years later, the debate still simmers, with new data only deepening the riddle. G2's story isn't just about a single odd object, it's a test case. If it does harbor a star, it challenges our assumptions about how many invisible stellar survivors might orbit the galactic center, unseen but shaping their environment. And if it's truly just a cloud, it forces us to rethink the durability of cosmic gas under extreme conditions. Either way, this cosmic enigma reminds us that near the heart of the Milky Way, reality often defies expectation, and what seems ordinary might be anything but. At the farthest edges of what we can observe, something impossible is happening: galaxy clusters racing toward an unfathomable horizon, as if the universe itself were tipping into an unseen abyss. Scientists call it the dark flow, and its very existence defies the foundational laws of cosmic motion. Imagine throwing a ball straight up, only to watch it suddenly veer sideways midair, tugged by an invisible force. Now picture that same mystery playing out on the grandest scale, with entire clusters of galaxies, thousands of them moving in unison toward a point beyond the cosmic light barrier, a place we can't see, map, or even fully comprehend. The discovery emerged from meticulous studies of the cosmic microwave background, the afterglow of the Big Bang. By analyzing subtle temperature shifts in this primordial light, researchers detected a peculiar pattern: clusters drifting at staggering speeds of nearly 1,000 kilometers per second in the same general direction, toward constellations Centaurus and Hydra. This wasn't random motion, it was a coordinated exodus, as if space itself were a river, and these galaxies were caught in its current. The kicker: no known structure in the observable universe has enough mass to generate such a pull. Theories to explain this anomaly range from tantalizing to mind-breaking. One possibility involves gravitational influence from a supermassive structure lurking in the unobservable universe, a region of space so distant its light hasn't had time to reach us since the dawn of time. Think of it as a cosmic neighbor hidden behind an eternal curtain, its gravity warping our reality like the shadow of a mountain just beyond the horizon. Skeptics argue it could be a statistical fluke or a flaw in our measurements, but the data persists across multiple studies, each reinforcing the same unsettling conclusion: something out there is pulling us. Then there's the wild card, the multiverse. Some physicists speculate the dark flow could be evidence of a neighboring universe brushing against our own, its gravity leaking through the fabric of space-time. It's a radical idea, suggesting our cosmos isn't just expanding but drifting, caught in an invisible tide from another reality entirely. Whether it's an unseen colossus or a crack in the cosmic egg, one thing's certain: the dark flow doesn't just challenge what we know about the universe. It hints at mysteries waiting outside it. Scattered across the Milky Way like celestial lighthouses without beams, the Magnificent Seven stand apart from every other neutron star we've found. These solitary cosmic remnants glow faintly in X-rays, radiating heat without the telltale pulses or dazzling companions we'd expect. Most neutron stars scream their presence with rapid rotations or violent stellar partnerships, but these seven, they're silent, steady, and utterly baffling. Take their temperatures for starters. Neutron stars should cool rapidly after their supernova births, fading into darkness within a few million years as their unimaginable heat bleeds into space. Yet the Magnificent Seven, despite being ancient by stellar standards, still burn at nearly 1,000,000 degrees, their surfaces shimmering with unexplained energy. It's as if someone left a stove on at full blast long after the kitchen should have gone cold. Where is this heat coming from? Some theorists argue hidden magnetic fields could be at work, slowly decaying and releasing energy like a battery losing charge. Others propose wilder ideas like exotic particles crystallizing in their cores, generating warmth through processes we've yet to imagine. Then there's the eerie absence of spin. Pulsars earn their name by whirling at dizzying speeds, their beams sweeping across Earth like cosmic metronomes. But these 7 drift almost motionless, their rotations so sluggish that a single day could last hours. Without rapid spins to generate electrical currents, their magnetic fields should be feeble, yet observations suggest otherwise. Some exhibit surface hotspots, localized regions blazing far hotter than their surroundings, hinting at magnetic activity with no clear source. Could there be fractures in their crusts, letting internal heat leak out? Or perhaps slow-motion quakes ripple across their surfaces, reigniting their glow like embers stirred in a dying fire? The plot thickens when you consider what's not their companions. Many neutron stars vampirically siphon gas from neighboring stars, creating brilliant accretion disks that light up in X-rays. The Magnificent Seven, though, float in perfect isolation, their emissions too steady to be fueled by stellar cannibalism. That leaves 2 possibilities. Either they once had partners and mysteriously lost them, or they've been solo from the start, a rarity in a universe where most massive stars form in pairs. Perhaps the most compelling clue lies in their spectra. When scientists analyzed the light from these objects, they found absorption features that didn't match any known element. Some speculate this could be evidence of proton superconductivity within the stars themselves, a state of matter so extreme it alters how light escapes their surfaces. Others wonder if we're seeing the fingerprints of hyper-dense atmospheres, layers of electrons crushed into quantum configurations alien to our textbooks. What makes the Magnificent Seven truly remarkable isn't just their defiance of expectations, it's what they reveal about the hidden diversity of stellar corpses. They might represent a missing link between pulsars and the universe's quietest neutron stars, a population we've barely begun to uncover. Or perhaps there's something else entirely, cosmic anomalies that rewrite the rules of how matter behaves under conditions we can't replicate. Each unanswered question is a reminder. Even the dead stars still have stories to tell, and the Milky Way's graveyards are far from silent. Hidden in the motions of millions of stars, astronomers uncovered a relic from one of the Milky Way's most violent encounters. The Gaia Sausage, a cosmic scar left by a dwarf galaxy torn apart and devoured nearly 10 billion years ago. This isn't just some ancient collision. It's the event that may have sculpted the very foundation of our galaxy's halo, imprinting its chaos into the orbits of stars we see today. The discovery came thanks to the Gaia Space Telescope, which mapped the precise movements of over 1 billion stars, revealing something astonishing. A population of stars wasn't moving randomly but streaming in radical, sausage-shaped orbits, all pointing back to a single cataclysmic moment in time. Picture this, a smaller galaxy, perhaps a tenth the Milky Way's mass, spiraling toward our nascent galactic disk in the early universe. Gravitational tides ripped it apart like cosmic taffy, its stars scattered into elongated paths that still trace the violence of their capture. These stars don't just move differently, they're chemically distinct, richer in alpha elements like oxygen and magnesium compared to the Milky Way's native population. It's as if we're tasting the fossilized remains of another world, its atomic signature preserved in stellar DNA. The collision didn't just add stars, it may have fundamentally reshaped our galaxy's structure, puffing up the halo into the diffuse cloud of stars we see today. But here's where it gets even wilder. The Gaia Sausage isn't alone. Some researchers believe it could be connected to other galactic oddities, like the Sequoia and Kraken dwarf galaxies, remnants of multiple mergers that built the Milky Way piece by chaotic piece. It's a cosmic version of forensic reconstruction, where stellar motions become clues to a past we can't observe directly. And the implications go beyond history. Understanding these collisions helps explain why our galaxy looks the way it does, from its thick disk to the oddball stars that don't belong. Perhaps most haunting is the realization that this violence isn't over. The Large Magellanic Cloud, a current satellite galaxy, is on course to merge with the Milky Way in a few billion years, an echo of the Gaia Sausage's fate. These collisions aren't aberrations, they're the universe's way of building galaxies, a cycle of destruction and rebirth written in starlight. So the next time you gaze at the night sky, remember, some of those faint points of light aren't just neighbors. They're survivors carrying the memory of a time when the Milky Way was remade by fire. Among the billions of stars drifting peacefully through the Milky Way, there exists a rare breed of cosmic fugitives, hypervelocity stars. These aren't your average suns lazily orbiting the galactic center. They're rogue bullets hurtling through space at speeds topping 1,000 kilometers per second, so fast they're escaping the galaxy entirely. Their origin story reads like a celestial crime scene. Something, somewhere, hurled them into the void with unimaginable force, and the prime suspect. Our very own supermassive black hole, Sagittarius A star, acting as a gravitational slingshot in the ultimate cosmic expulsion. Take one of the most famous examples, star S5 HVS1, first spotted racing toward intergalactic space at over 6 million miles per hour. Tracing its path backward leads directly to the galactic center, the black hole's front door. The math tells a violent tale. This star was once part of a binary system that wandered too close to Sagittarius A star. As the black hole's gravity seized one star, the other was flung outward like a stone from a sling, gaining enough speed to break free from the Milky Way's gravitational grip entirely. It's a phenomenon astronomers call the Hill's mechanism, and it's the universe's most extreme form of stellar eviction. But not all hypervelocity stars come from the same dramatic origin. Some might be survivors of dwarf galaxies torn apart by the Milky Way's tides, their stars sent careening into the void as collateral damage. Others could be the result of supernova explosions in binary systems, where one star detonates with such asymmetry that it kicks its companion into hyperspace. The strangest candidates, though, are the so-called empty hypervelocity stars, objects like HVS3, which moves like it was ejected from the galactic center but lacks the chemical fingerprints of stars born there. These outliers hint that our black hole might not be the only thing launching stars into the abyss. Could there be undiscovered mid-mass black holes lurking in the galaxy's spiral arms, capable of similar gravitational cannon fire? Here's where it gets even weirder. A handful of hypervelocity stars aren't fleeing the Milky Way, they're invading it. These intergalactic interlopers, like star J1124+0930, are moving so fast they couldn't have originated in our galaxy at all. Their trajectories suggest extragalactic origins, perhaps ejected from the Large Magellanic Cloud or even more distant neighbors. Imagine a star catapulted across millions of light years, only to end up as a fleeting tourist in our cosmic backyard. The real mystery: some hypervelocity stars shouldn't exist based on their speed alone. Calculations show the Milky Way's black hole can't accelerate stars beyond a certain velocity threshold, yet a few outliers defy even those limits. This has led to wild theories, like the possibility of stars being flung not just by gravity, but by the recoil of gravitational waves during black hole mergers. Or perhaps they're relics of a time when Sagittarius A star was more active. It's younger, hungrier, self-capable of launches we can't replicate today. Whatever their origins, hypervelocity stars are more than just celestial curiosities, they're living probes. Their trajectories map the invisible gravitational field of the galaxy, revealing dark matter's pull in ways static stars never could. Some might even carry planetary hitchhikers, frozen worlds torn from their birth systems and condemned to an eternal journey through the intergalactic dark. And one day, far in the future, these runaway stars will be the only evidence the Milky Way ever existed, drifting alone in the void long after our galaxy has merged into oblivion. They're the universe's way of reminding us no star is truly anchored, and in the grand cosmic dance, even the most stable orbits can be broken. As the large Magellanic Cloud drifts around the Milky Way, it doesn't sail through empty space, it plows through an invisible sea of dark matter, leaving a turbulent wake in its path like a ship cutting through cosmic waters. This ghostly trail, stretching across a staggering 200,000 light-years, isn't something we can photograph or directly observe. Instead, astronomers detected it by studying the subtle tug it exerts on the motions of stars in our galaxy's outskirts, revealing the fingerprints of an unseen force reshaping the fabric of our galactic neighborhood. The wake's existence confirms something theorists long suspected. Dark matter isn't just a static halo surrounding galaxies. It's dynamic, responsive, capable of swirling and clumping under gravitational disturbances. When the LMC, a satellite galaxy 1/10 the Milky Way's mass, orbits our galaxy, its gravity displaces this dark matter, creating ripples akin to waves stirred by a passing speedboat. But here's what stunned scientists: the wake's shape defied models. Instead of a smooth, symmetrical trail, it's lopsided and fragmented, suggesting the dark matter halo might be denser or more structured than we ever imagined. What's truly bizarre is how this discovery flips the script on galaxy interactions. For decades, we assumed the Milky Way's gravity dictated the LMC's fate, pulling it inexorably toward a future merger. But the wake reveals the opposite: the LMC is also tugging back, warping our galaxy's dark matter scaffolding with enough force to subtly alter the trajectories of distant stars. It's a gravitational dance where both partners lead, a give and take hidden in plain sight. The implications ripple beyond mere curiosity. If dark matter can be stirred this way, it might explain oddities in other satellite galaxies' orbits, or even why some stars in the Milky Way's halo move faster than predicted. Some researchers speculate the wake could be funneling dark matter particles into denser streams, potentially making them easier to detect in underground experiments hunting for these elusive particles. Others wonder if similar wakes trail other satellite galaxies, weaving a hidden web of dark matter currents throughout the cosmos. One thing's certain: this wake is temporary. In a few billion years, as the LMC spirals closer to the Milky Way, tidal forces will shred it apart, its stars and dark matter bleeding into our galaxy's halo. Until then, its ghostly imprint serves as a rare window into the invisible forces binding the universe, proof that even the darkest corners of space can't hide their secrets forever. Deep in the Orion Arm, one of the Milky Way's bustling spiral branches, lies a cosmic anomaly that's baffled scientists for decades, a patch of space where cosmic rays bombard the surrounding area with inexplicable intensity. Unlike typical hotspots which flare around supernova remnants or pulsars, this region offers no visible culprit. It's as if the universe turned an invisible particle accelerator toward Earth, and no one knows who flipped the switch. Cosmic rays, high-energy protons and atomic nuclei racing through space, usually originate from violent events like exploding stars or active black holes. But when researchers mapped the radiation pouring from this mystery spot, something didn't add up. The energy signature was all wrong. The rays here pack a punch far beyond what nearby supernova could produce, yet scans reveal no recent stellar explosions or collapsed cores in the area. Even more puzzling, the particles arrive in odd clusters, as if something's flickering on and off in the void, spraying bursts of energy like a celestial lawn sprinkler. One theory suggests we might be seeing the echo of a long-dead stellar giant. Imagine a massive star that collapsed quietly, without the fanfare of a supernova, leaving behind a black hole or neutron star shrouded in such thick dust that its radiation is absorbed except for these ultra-powerful cosmic rays which pierce through the veil. Another idea points to a hidden pulsar wind nebula, where a spinning neutron star's magnetic field acts like a cosmic slingshot, hurling particles to near light speeds. But if that's the case, why don't we detect the telltale gamma rays or radio waves that typically accompany such objects? Then there's the wild card, dark matter annihilation. Some physicists speculate this could be the signature of elusive dark matter particles colliding and disintegrating in deep space, releasing energy in sporadic bursts. It's a tantalizing thought that we might be glimpsing the invisible scaffolding of the universe unraveling in real time. Yet without definitive proof, the Orion Arms mystery spot remains just that, a riddle wrapped in radiation, daring us to look closer. What's clear is that this region defies the textbook explanations. It forces us to question whether we're missing entire chapters in our understanding of particle acceleration, or if the cosmos is quietly running experiments we haven't even imagined. Every unanswered question is a reminder. Sometimes the most profound discoveries begin not with a flash, but with a whisper of something we can't yet see. Hidden among the familiar glow of the Milky Way's red giants, astronomers recently stumbled upon a group of elderly stars behaving in ways no one predicted, dubbed the Old Smokers. These aren't your typical aging suns quietly burning out. Instead, they periodically erupt, belching thick clouds of smoke like dust into space like celestial chimneys, shrouding themselves in veils so dense they vanish from view for years at a time. It's a cosmic magic act no one saw coming, forcing us to rewrite the playbook on how stars spend their final years. The discovery happened almost by accident. Scientists monitoring the galactic bulge, the crowded heart of the Milky Way, noticed a handful of red giants dimming dramatically, their light flickering as if something was smothering them. At first, they assumed these were ordinary variable stars or perhaps eclipsing binaries, but the truth was far stranger. These stars weren't being obscured by external objects. They were creating their own obscurity, puffing out towering plumes of carbon-rich dust that condensed around them like a fog. Imagine a star coughing up its own atmosphere, not in a violent explosion, but in slow, rolling waves. A stellar ember exhaling smoke rings into the void. What makes Old Smokers truly bizarre is their timing. Most dying stars shed material in predictable cycles, but these giants go quiet for decades, even centuries, before suddenly erupting without warning. One theory suggests their interiors may harbor unstable layers where helium fusion flickers on and off, triggering seismic waves that jolt dust-forming elements to the surface. Picture a boiling pot with a loose lid. Pressure builds unevenly until, whoosh, a burst of steam escapes, only to settle back into silence. The implications ripple far beyond curiosity. For decades, astronomers assumed the Milky Way's interstellar dust, the raw material for new stars and planets, came primarily from supernova or stellar winds. Old Smokers flipped that narrative, revealing a hidden conveyor belt of dust production in the galaxy's twilight stars. Their eruptions could be seeding regions like the galactic bulge with heavy elements, quietly shaping the chemistry of future cosmic generations. Then there's the bigger mystery. Why now? These stars aren't rare. We just missed them because their dimming phases were mistaken for data glitches or foreground interference. It begs the question, how many other celestial phenomena are hiding in plain sight, overlooked because they don't fit our expectations? The Old Smokers are a humbling reminder. The universe often reserves its greatest surprises not in the distant, exotic extremes, but in the quiet, familiar corners we thought we knew. And as these aging giants continue their slow, smoky dance, they challenge us to reconsider not just how stars die, but how they transform, leaving their mark on the galaxy long after their light fades. At the heart of our galaxy, hidden behind thick curtains of dust and starlight, lies an architectural marvel most spiral galaxies shouldn't have: the X-shaped bulge. Picture the Milky Way's core not as a simple sphere of stars, but as a colossal, glowing X suspended in space, its arms stretching diagonally from a central bar like cosmic wings. This bizarre structure, spanning over 10,000 light-years, defies the standard blueprints of galactic design. most bulges are round or squashed like footballs, but ours. It's a puzzle box, its very shape whispering secrets about violent mergers and chaotic rebirths from the distant past. The discovery unfolded like a detective story. Astronomers first inferred the X shape not by seeing it directly. Our view of the core is too obscured, but by studying the motions and distributions of red giant stars. These ancient suns, acting like breadcrumbs, traced a pattern no one expected. Their orbits aligned along distinct diagonal streams, crossing at the center like an hourglass tipped on its side. Computer simulations revealed the likely culprit: an ancient collision. Billions of years ago, a smaller galaxy likely plowed into the nascent Milky Way, its gravity warping the central bar into this striking X. The violence didn't just reshape the bulge, it may have triggered waves of star formation, embedding the evidence in stellar chemistry we're only now deciphering. Here's where it gets stranger. The X isn't static. Stars within it oscillate vertically as they orbit, creating a dynamic, almost breathing structure. Some researchers compare it to a sloshing bowl of water, where gravitational forces cause stars to rise and fall in sync. This motion suggests the bulge isn't just a fossil, it's alive, its form actively maintained by the Milky Way's rotation and dark matter halo. Yet the real enigma lies in its asymmetry. One side of the X appears slightly longer than the other, a lopsidedness that hints at yet another unresolved drama, perhaps a second, later merger that tugged the structure off kilter. The implications ripple beyond curiosity. The X-shaped bulge challenges the textbook model of how galactic centers evolve. It suggests our galaxy didn't grow quietly, but through a series of violent encounters, each leaving scars in the stars. Some theories even propose the bulge's unique shape could influence how stars migrate across the Milky Way, funneling them from the inner regions outward like a cosmic turnstile. And if mergers sculpted our galaxy's heart, it raises a haunting question: how many other X-shaped bulges are out there, hidden in plain sight, waiting to rewrite our understanding of galactic adolescence? What's most humbling is realizing we're seeing this structure from the worst possible angle, edge-on, from within the Milky Way's disk. If we could view it face-on, the X might shine as clearly as a celestial insignia. Instead, we piece together its ghostly outline through painstaking observations, a reminder that even our own galaxy keeps its grandest designs just out of sight. The bulge isn't just a relic, it's a living archive, its stars carrying the memory of collisions that shaped the Milky Way into the spiral we call home. And somewhere in that tangled starlight, the next chapter of our galaxy's story waits to be read. Globular clusters should be the last place you'd expect a cosmic mystery. These dense balls of ancient stars, each packed with hundreds of thousands of suns, are supposed to be textbook examples of predictable celestial mechanics. But lurking among them are oddballs like M53, a glittering swarm of stars in the constellation Coma Berenices that defies the rules. Unlike typical globulars, which orbit galaxies wrapped in dark matter like invisible cloaks, M53 and its kin seem to have misplaced theirs entirely. It's as if someone reached into these clusters and stripped away the universe's most abundant and most mysterious ingredient, leaving astronomers scratching their heads over how such a structure could even exist. The puzzle starts with motion. Stars in globular clusters dance around their cores, their speeds dictated by gravity. Normally, that gravity comes from two sources: the visible stars themselves and the unseen dark matter halo surrounding them. But when researchers measured the velocities of stars in M53, the math didn't add up. The stars moved too slowly for the cluster's mass, unless, that is, dark matter was conspicuously absent. It's like watching children spin on a merry-go-round that's missing its central axle. Without the hidden counterbalance, their motions make no sense. Follow-up studies of other dark, less globulars only deepen the mystery. These clusters aren't rare exceptions, they're a distinct population, scattered across the Milky Way's halo like cosmic riddles. So where did their dark matter go? One theory suggests these clusters weren't born around our galaxy at all. They might be the stripped cores of dwarf galaxies that wandered too close to the Milky Way eons ago, their outer layers and dark matter shredded by tidal forces. Picture a peach pit left behind after the fruit is devoured. The dense stellar core remains, but the surrounding mass is gone. Supporting this idea, some of these odd clusters, like Omega Centauri, contain multiple generations of stars, a hallmark of galaxies, not typical globulars. But there's a twist. Not all dark matter-deficient clusters show signs of a galactic origin. Some, like M53, have stellar populations too uniform to fit the dwarf galaxy narrative. This has led to a radical alternative. Perhaps these clusters formed in regions of the early universe where dark matter was strangely scarce. Imagine pockets of primordial gas collapsing without the usual gravitational scaffolding, birthing stars in unnaturally clean environments. If true, they'd be cosmic fossils from an era when dark matter wasn't as evenly mixed as we thought, a revelation that could rewrite our understanding of the universe's infancy. The implications stretch beyond these clusters. If dark matter isn't just missing but was never there, it challenges the bedrock assumption that all structures in the universe rely on its gravitational glue. Even more provocative, some researchers speculate these anomalies might hint at a flaw in our models of gravity itself, not enough to overthrow dark matter entirely, but enough to suggest that its behavior is far weirder than we've imagined. Every time we point telescopes at these celestial paradoxes, they whisper the same unsettling question: what if the universe's rules aren't as universal as we thought? Stretching across the Milky Way like a sine wave frozen in space, the Radcliffe wave isn't just a gas cloud, it's a celestial heartbeat, pulsing with the rhythm of newborn stars. Discovered in 2020 by astronomers combing through Gaia satellite data, this mammoth structure arcs 9,000 light-years through our galactic neighborhood, cresting just 500 light-years above and below the plane of the Milky Way's disk. Imagine a serpent of gas and dust slithering through the spiral arm, its peaks and troughs dotted with stellar nurseries where suns ignite in synchronized bursts. This isn't random chaos, it's star formation as a choreographed performance, with the wave itself acting as both stage and conductor. What makes this structure so mesmerizing isn't just its size, it's the uncanny precision of its undulations. The Radcliffe wave isn't a static relic, it oscillates much like a guitar string vibrating through space. Stars along its length move in harmony, bobbing up and down as they orbit the galactic center, their motion revealing the wave's gravitational pull. But here's the puzzle: such perfect oscillations shouldn't survive long in the turbulent Milky Way. Galactic tides and passing molecular clouds should have shredded it eons ago. Yet somehow this delicate filament persists, its structure eerily intact for millions of years. The secret might lie in its star-forming factories. The wave's crests, regions where gas is densest, coincide with familiar stellar nurseries like the Orion Nebula, while its troughs remain quieter, their gas too diffuse for stars to ignite. This alternating pattern suggests the wave isn't just a backdrop for star birth. It's an active participant, compressing gas as it moves to trigger stellar ignition like a cosmic conveyor belt. Every time the structure's undulation squeezes a gas pocket, pressure builds until boom, a new star cluster flares to life. Yet the origins of this cosmic ripple remain hotly debated. Some simulations suggest the Radcliffe wave could be the aftermath of a dwarf galaxy sideswiping the Milky Way, its gravitational wake disturbing the galactic disk like a stone dropped in a pond. Others propose it's a standing wave, a natural resonance in the galaxy's gravitational field, much like vibrations humming through a wineglass, the wildest theory. That it's a fossilized spiral arm, a remnant from when the Milky Way was younger and its structure less orderly, preserved by some quirk of orbital dynamics. What's undeniable is the wave's influence. Its stellar nurseries have birthed many of the bright stars we see tonight. their light a testament to the structure's quiet power. And as telescopes peer deeper, they've found something even stranger. The wave seems connected to other gaseous filaments, hinting at a vast, hidden skeleton threading through the galaxy. We might be looking at just one ripple in a cosmic sea of undulating structures, their rhythms dictating where and when the next generation of stars will shine. This isn't just a curiosity, it's a paradigm shift. For decades, astronomers assumed star-forming regions were isolated islands. The Radcliffe wave proves they're part of something grander, a symphony of gas and gravity playing out on scales we're only beginning to grasp. And somewhere in its undulations, there's a clue to how galaxies like ours turn raw chaos into the ordered beauty of spirals. One thing's certain, the Milky Way isn't just a collection of stars. It's a living, breathing entity, its pulse written in the rise and fall of this ancient star-making wave. Dotted around the Milky Way like scattered emeralds in a cosmic treasure hunt, the green pea galaxies defy every expectation of what a dwarf galaxy should be. These tiny, brilliant specks, no larger than a fraction of our galaxy's size, pack a staggering punch, churning out new stars at rates that put even the busiest spiral arms to shame. Named for their vivid green hue in telescope images, a quirk of their intense oxygen emissions, they glow like radioactive jewels against the dark canvas of intergalactic space. But what really astonishes astronomers isn't just their color, it's the fact they exist in our galactic backyard at all. Green peas were first discovered in deep field surveys of the distant universe, relics of an era 10 billion years ago when starburst galaxies were common. Finding them orbiting the Milky Way was like stumbling upon a living dinosaur, a relic from the cosmos's wild youth, inexplicably preserved in the modern day. Their star formation is so ferocious, it would be like cramming all the suns of the Orion Nebula into a space no bigger than the small Magellanic Cloud. Yet somehow, these tiny powerhouses sustain this frenzy without tearing themselves apart, a feat that challenges our understanding of how galaxies regulate their growth. The secret lies in their chemistry. Unlike typical galaxies where heavy elements are diluted across vast volumes, green peas concentrate oxygen and other alpha elements into dense, glowing pockets. This isn't just a minor quirk, their spectra blaze with emission lines so strong, they drown out the signal of a galaxy 100 times their size. Some researchers believe this intensity stems from their youth. They might be first-generation galaxies late to the cosmic party, their gas so pristine it fuels star birth with unmatched efficiency. Others argue they're the survivors of violent mergers, their gas compressed by ancient collisions into these compact, glowing knots. But here's the twist, their location makes no sense. Dwarf galaxies in the Milky Way's halo are supposed to be quiet, starved of gas, their star-forming days long behind them. Green peas break all the rules, blazing with activity in regions where the ambient radiation should have stifled their birth clouds eons ago. One theory suggests they're refugees, ejected from galactic collisions with enough gas to keep their furnaces burning. Another posits they're feeding on hidden reservoirs of cold gas, siphoned from the Milky Way's own halo like cosmic thieves tapping a forbidden well. What's undeniable is their impact. These tiny galaxies act as laboratories, offering a glimpse into conditions that prevailed when the universe was in its infancy. Their oxygen-rich outflows might even seed future star formation, their heavy elements destined to end up in planets, and perhaps life billions of years from now. And as telescopes uncover more of these emerald oddities, they're revealing a startling truth. The Milky Way's quiet halo might be teeming with fireworks waiting for us to look closer. The green peas aren't just celestial curiosities, they're proof that even in the darkest corners of space, the universe keeps a few surprises up its sleeve. Somewhere between the stellar mass black holes born from collapsing stars and the supermassive giants anchoring galactic centers, there should exist a cosmic middle child, intermediate black holes weighing thousands of suns. Astronomers call them the missing link, crucial stepping stones in how black holes grow from modest to monstrous. Yet here's the twist: despite decades of searching, the Milky Way seems to have misplaced them entirely. It's like finding a family photo where all the toddlers are absent, only babies and adults staring back at you, leaving a glaring gap in the story of how giants are born. Take the case of Omega Centauri, our galaxy's largest globular cluster. Hubble observations revealed stars at its core whirling at dizzying speeds, hinting at an unseen mass of roughly 40,000 suns, exactly the heft expected for an intermediate black hole. But deeper scrutiny left researchers empty-handed. No X-ray flares, no telltale radio signatures, nothing but gravitational breadcrumbs leading to a phantom. Similar dead ends unfolded in other promising candidates, from dense star clusters to ancient stellar streams. These black holes aren't just hiding, they've seemingly skipped our galaxy altogether, despite simulations insisting they must exist. What's going on? One possibility is that intermediate black holes are cosmic introverts, devouring so little surrounding matter they emit almost no detectable radiation. Unlike their supermassive cousins, which feast loudly on gas and stars, these middleweights might sustain themselves on sparse interstellar crumbs, glowing too faintly for our telescopes to catch. Others argue they're simply in the wrong neighborhoods, ejected from star clusters by gravitational kicks during mergers, now drifting invisibly through galactic voids. Then there's the darker scenario: maybe they never formed in the first place. Current models suggest intermediate black holes grow either by merging smaller black holes or from the direct collapse of massive primordial gas clouds in the early universe. If conditions in the Milky Way prevented both pathways, say, by breaking apart nascent clusters before mergers could occur, we might be living in a cosmic oddity, a galaxy that somehow missed a universal phase of black hole adolescence. But don't count them out just yet. Recent studies of hypervelocity stars hint at unseen gravitational slingshots in the galactic halo, possibly flung by stealthy mid-sized black holes. And in 2021, gravitational wave detectors picked up ripples from a merger involving an 85 solar mass black hole, too hefty for a stellar collapse, yet too small for supermassive status. Could this be the first whisper of our missing link? The hunt continues, not just for the objects themselves, but for the answer to a deeper question. Is the Milky Way's black hole family tree incomplete, or are we just reading it wrong? Every empty search teaches us something new about black holes, galactic evolution, and the humbling reality that sometimes the universe's quietest players are also its best at hide and seek. Buried in the cosmic archives of our galaxy's past, there's a tantalizing crime scene, evidence that the Milky Way might have once been home to not one, but two supermassive black holes. The potential culprit, a gravitational brawl so violent, it sent one of these monsters hurtling into intergalactic space at speeds topping 4 million miles per hour. This isn't just theoretical drama. Astronomers have spotted trails of stars stretching like cosmic breadcrumbs from the galactic center, their paths hinting at an unthinkable event, a supermassive black hole flung from its throne like a celestial exile. The clues start with the stars themselves. Near Sagittarius A, our resident black hole, there's a peculiar cluster of suns orbiting in a tight disk, but just outside this orderly arrangement, another group moves erratically, as if yanked by an invisible force. Simulations reveal this chaos matches exactly what you'd expect if a second black hole, perhaps thousands of times the mass of our Sun, had once lurked nearby before being catapulted outward. Picture two titans circling each other in a deadly dance, their gravity warping space until one absorbed enough energy to break free entirely, a cosmic slingshot powered by the universe's most extreme physics. Here's where it gets wilder. If such a black hole was ejected, it wouldn't have left quietly. The recoil from such an event would have sent shockwaves through the galaxy, potentially triggering bursts of star formation or even distorting the Milky Way's spiral arms. Some researchers speculate this could explain odd structures in our galaxy's halo, fossilized ripples from the moment the black hole punched its way out. Others suggest it might still be out there, drifting invisibly through the galactic outskirts, its presence betrayed only by the occasional flicker of stars tugged from their usual path. But how could something so monstrous go missing? The answer lies in black hole mergers. When two supermassive black holes spiral toward collision, they don't just merge smoothly, they recoil. Gravitational waves, the ripples in spacetime predicted by Einstein, carry away momentum asymmetrically, sometimes kicking the newly formed black hole clear out of its host galaxy. For the Milky Way, that might mean losing a sibling to the void, a ghost now wandering the dark. The implications ripple beyond curiosity. If true, this runaway black hole could rewrite our understanding of galactic evolution. Most large galaxies are thought to grow by cannibalizing smaller ones, each merger depositing a fresh black hole into their cores. But if mergers can also eject them, it might explain why some galaxies, including ours, appear to have fewer supermassive black holes than expected. It's a cosmic balancing act. For every monster that settles in, another might be sent packing. And here's the twist: we might not have to search far to find it. Recent studies suggest this rogue black hole could still be lurking much closer than we think, perhaps just a few thousand light years from the galactic center, its gravity subtly bending the paths of nearby stars. If caught, it would be the ultimate prize, a relic from the Milky Way's most violent chapter, a fugitive carrying the secrets of how galaxies are forged in chaos. Until then, its absence remains a gaping hole in our cosmic story, one that challenges us to keep looking, because sometimes the universe's greatest mysteries aren't what's there but what's missing. Rising from the Milky Way's heart like twin volcanoes of pure energy, the galactic geysers blast charged particles into the void at speeds approaching the speed of light, a spectacle spanning 50,000 light-years, dwarfing even the Fermi Bubbles in sheer scale. Discovered in 2019 by astronomers mapping gamma-ray emissions, these colossal jets punch through the galaxy's disk, carving invisible channels through the interstellar medium and painting the halo with ghostly X-ray signatures. But what's truly baffling isn't their size, it's the fact that their power source remains utterly unknown. The leading suspect, of course, is Sagittarius A, our galaxy's supermassive black hole. But here's the catch: this cosmic behemoth is practically dormant today, its appetite for matter a mere flicker compared to the voracious feeding of active galactic nuclei. For these geysers to originate from Sagittarius A, something must have jump-started it in the relatively recent past, like a sleeping giant briefly roused by a stellar snack. Some models suggest a rogue gas cloud or star wandered too close a few million years ago, triggering a short-lived feeding frenzy that spat out these jets as a cosmic afterburner. Yet there's no smoking gun in the black hole's vicinity, no debris field or stellar wreckage to corroborate the theory. Another possibility is even wilder. The geysers might not be the work of Sagittarius A at all, but the collective output of thousands of pulsars and stellar remnants near the galactic center. Imagine a swarm of neutron stars, each firing particle beams like microscopic blowtorches, their combined energy aligning along magnetic field lines to create these monstrous structures. It's a cosmic choir where every voice harmonizes into a deafening roar, except observations show the geysers' energy distribution doesn't quite match this scenario. Their gamma-ray signatures are too uniform, too focused, as if sculpted by a single, unimaginably powerful hand. Then there's the matter of their shape. Unlike the symmetrical Fermi bubbles, the geysers twist and filament, their structures braided like celestial ropes. This suggests turbulent magnetic fields are at play, wrangling the particles into coherent streams over mind-boggling distances. Some researchers compare them to gargantuan particle accelerators, natural versions of the Large Hadron Collider stretched across the galaxy, where magnetic reconnection events, sudden snaps in field lines, launch particles to near light speed. If true, they could be the source of some ultra-high-energy cosmic rays that bombard Earth, their origins tracing back to the Milky Way's turbulent core. What's most unsettling is their ephemeral nature. These geysers might be fleeting on cosmic timescales, their particles destined to dissipate into the galactic halo within a few million years. We could be witnessing a rare, violent phase in the Milky Way's life cycle, one that suggests our quiet galactic home might have a far more explosive past than we ever imagined. And lurking in their ghostly glow is a tantalizing question. If this is what our galaxy can do while napping, what happens when it truly wakes up? Deep in the constellation Musca, nestled within the swirling arms of the Milky Way, two cosmic corpses are locked in a gravitational tango so bizarre it shouldn't exist. Meet PSR J1141 6545, a neutron star and white dwarf duo orbiting each other at breakneck speeds. Their dance steps so out of sync with Einstein's playbook that physicists first dismissed the data as an instrument glitch. This isn't just another binary system, it's a celestial rebellion challenging our most sacred assumptions about how gravity works on the grandest scales. The neutron star, a pulsar spinning an insane 150 times per minute, beams radio waves toward Earth with metronomic precision, acting as nature's most accurate stopwatch. Its partner, a white dwarf the size of Earth but packing half the Sun's mass, should, according to every textbook, orbit in a near-perfect ellipse, their mutual gravity dictating a predictable rhythm. But here's where reality diverges from theory. Their orbital plane isn't static. It wobbles, processing at a rate 4 times faster than general relativity predicts. It's like watching a spinning top gradually tilt on its axis, except this top weighs more than our Sun and defies the very equations meant to describe it. For decades, physicists assumed such extreme systems would conform to Einstein's framework. After all, general relativity has survived every test from Mercury's orbit to gravitational wave detections. Yet PSR J1141 6545's misbehaving orbit suggests something might be missing, perhaps an unseen interaction between the white dwarf's distorted shape and the pulsar's intense gravitational field. Picture the white dwarf as a slightly squashed sphere, its equator bulging from rapid rotation during its stellar youth. That asymmetry, combined with the pulsar's gravity, could create a torque powerful enough to yank the entire orbital plane off kilter. But simulations show this effect shouldn't be nearly strong enough to explain the observed wobble. Then there's the wild card, frame dragging. According to general relativity, massive rotating objects like the pulsar should drag space-time around with them like a spoon stirring honey. This subtle effect has been measured around Earth, albeit weakly, by satellites like Gravity Probe B. But in PSR J1141 6545, the pulsar's spin and the white dwarf's orbit align in a way that amplifies frame dragging to unprecedented levels. Could this be the smoking gun, proof that extreme gravity operates differently than we thought? Or is there an even stranger force at play, something beyond our current models, like a hint of quantum gravity manifesting at macroscopic scales? The system's backstory only deepens the intrigue. Billions of years ago, before these stellar remnants existed, they were likely a typical binary pair, two main sequence stars orbiting peacefully. When the more massive one exploded as a supernova, its core collapsed into the pulsar we see today. The kick from that explosion should have sent the system careening apart, yet somehow they stayed bound, and the surviving star later swelled into a red giant, dumping material onto the pulsar and spinning it up to its dizzying speed before collapsing into today's white dwarf. This violent past might hold clues to their current oddities, a fossil record of interactions that warped spacetime itself. What's truly electrifying is how this cosmic oddball could redefine physics. If the discrepancy stems from general relativity's limitations, it might point toward a grander theory, one that reconciles gravity with quantum mechanics. Alternatively, it could reveal new facets of neutron star interiors, where matter crushes into exotic states beyond protons and neutrons. Every pulse from this system is a coded message, a challenge flung across the cosmos. Figure me out if you can. For now, Pulsar J 1141-6545 remains an enigma wrapped in a paradox, its existence both a thorn in theorists' sides and a beacon for discovery. It's a reminder that the universe doesn't care about our textbooks, it writes its own rules, and sometimes it lets us catch a glimpse of the ink still wet on the page. Far from the bustling stellar nurseries and glowing nebulae, the Milky Way harbors a shadowy secret, vast, starless clouds of hydrogen drifting like silent ghosts through the cosmic void. These aren't the vibrant, star-forming regions we're used to seeing. They're dark, isolated, and eerily empty, their existence betrayed only by the faintest whisper of radio waves as their hydrogen atoms hum in the cold depths of space. Yet within these quiet giants could lie the seeds of future suns, frozen blueprints waiting for the right conditions to ignite. Think of them as cosmic lumberyards, piles of raw material stacked and forgotten, untouched by the sparks that would set them ablaze. Unlike typical molecular clouds, which collapse under their own gravity to birth stars, these dark hydrogen clouds remain mysteriously dormant. Some stretch hundreds of light years across, their masses rivaling small galaxies, yet not a single star flickers within them. It's as if the universe pressed pause on their evolution, leaving them suspended in a state of perpetual potential. The question is why. One clue lies in their extreme isolation. Most star-forming clouds are jostled by nearby supernova or galactic spiral arms, their gas stirred into turbulence that triggers collapse. These dark clouds, though, float in the galactic equivalent of deserted backroads, too far from any disruptive force to crumple into stars. Without external pressure or internal turbulence, their hydrogen remains diffuse, like a mist too thin to condense into raindrops. Yet simulations suggest they might not stay quiet forever. A passing shockwave from a distant supernova or even a galactic collision could be all it takes to send them tumbling into action, compressing their gas into the dense knots where future stars will flicker to life. But here's the twist: some of these clouds aren't just dormant, they're primordial, their chemistry nearly untouched since the early universe. Spectroscopy reveals a startling lack of heavy elements: oxygen, carbon, iron, the usual pollutants from generations of dead stars. That makes them cosmic time capsules, preserving hydrogen in its purest form, just as it existed billions of years ago before stars forged the elements that now fill our galaxy. If they ever do collapse, the stars they form would be unlike any we see today: blindingly bright, short-lived giants composed almost entirely of hydrogen and helium, mirroring the first stars that illuminated the infant cosmos. And then there's the dark matter factor. Some of these clouds are so massive, their gravity can't be explained by hydrogen alone. Hidden halos of dark matter might cradle them, their invisible pull preventing the gas from dissipating into the galactic wind. It's a tantalizing thought that these starless clouds could be wrapped in the same shadowy shroud that shapes galaxies, a hidden link between the seen and unseen universe. What's most humbling is realizing how much of the galaxy's story remains unwritten. These dark clouds are placeholders, cosmic blank pages waiting for the universe to pick up the pen. They remind us that star formation isn't just about what's happening now. It's about what could happen given time and the right nudge from the cosmos. And somewhere out there, in the silence between the stars, the next chapter of the Milky Way's evolution is quietly taking shape. beneath the placid glow of dying stars, a celestial alchemy unfolds, one where the very air turns to diamonds. Not the tiny gems we prize on Earth, but mountain-sized crystals raining through the atmospheres of white dwarfs in a phenomenon astronomers poetically call crystal rain. Imagine a world where snowstorms aren't made of water, but carbon compressed into glittering lattices, each flake a diamond vast enough to dwarf Everest. This isn't science fiction, it's the fate awaiting stars like our Sun once they exhale their final breaths and collapse into these dense, Earth-sized embers. The magic begins when a white dwarf cools. After shedding its outer layers as a planetary nebula, the exposed core, a searing mass of carbon and oxygen, slowly dims over billions of years. As temperatures plummet below 50,000 degrees, something extraordinary happens. The carbon in its atmosphere starts to crystallize. Picture a pot of molten sugar left too long on the stove, hardening into rock candy. In the microgravity of a white dwarf, these carbon crystals don't just form, they precipitate, sinking toward the star's core in a slow-motion, shimmering avalanche. Telescopes have caught hints of this process in the spectra of ancient white dwarfs, their light dimming at regular intervals as diamond storms drift across their surfaces like cosmic weather fronts. What's baffling is the scale. These aren't microscopic crystals. Simulations suggest they could grow to hundreds of kilometers wide, their structures forged under pressures 1,000,000 times greater than Earth's crust. Some white dwarfs might even harbor entire layers of crystallized carbon just beneath their atmospheres, like planetary-scale diamond mantles waiting to be uncovered. The irony is exquisite. Stars that once fused carbon in their cores now wear it as jewelry, their very essence reforged into the universe's most dazzling tombstones. Yet the real surprise isn't the diamonds, it's the silence. White dwarfs with crystal rain show bizarrely clean spectra, almost devoid of atmospheric contaminants. The explanation: as the carbon crystallizes, it drags heavier impurities like oxygen and metals down with it, effectively purifying the star's upper layers. It's a self-cleaning oven on a cosmic scale, scrubbing its own atmosphere with every glittering snowfall. This discovery upends how we model stellar evolution, proving that dead stars aren't static relics but active chemists, still transforming themselves long after their fires burn out. The most tantalizing twist: these diamonds may not stay buried forever. If a white dwarf orbits a companion star, it might siphon enough material to reignite nuclear fusion in a cataclysmic explosion, a Type Ia supernova. In that blinding instant, the star's crystalline treasure trove would be vaporized, scattering carbon and other elements across the galaxy. Every diamond forged in those ancient atmospheres could become the raw material for new stars, planets, or even life. So the next time you admire a gemstone sparkle, remember, somewhere in the Milky Way, there's a dead star spinning a diamond tapestry vaster than human imagination, its silent storms rewriting the rules of stellar afterlife. And one day, trillions of years from now, the last white dwarfs in the universe will freeze solid, their cores transforming into crystalline spheres, the ultimate cosmic monuments to entropy's slow, glittering victory. Stretching across the southern sky like a celestial serpent, the Phoenix stellar stream tells a story that shouldn't be possible, a river of stars born not once but twice. Discovered winding through the Milky Way's halo, this glittering trail was initially thought to be just another torn-apart globular cluster, its stars destined to fade into the galactic background. But when astronomers analyzed its starlight, they found something extraordinary. Mixed among the ancient suns were infants, stellar newborns glowing blue against the cosmic dark, defying every rule about how such streams form. Most stellar streams are cosmic graveyards, relics of clusters or dwarf galaxies shredded by the Milky Way's gravity, their stars pulled into long, mournful arcs as they dissolve into our galaxy. The Phoenix stream follows this pattern at first glance, a band of stars tracing an orbit around our galaxy's outskirts, but the devil's in the spectral details. While typical streams contain stars all born around the same time, Phoenix's population splits sharply between ancient red giants and young, hot blue stars barely 100 million years old. It's like finding dinosaur bones alongside smartphones, two eras that should never coexist. This anomaly sparked a detective story worthy of cosmic Sherlock Holmes. The leading theory suggests Phoenix wasn't just disrupted, it was resurrected. Originally a dwarf galaxy or massive cluster, its first generation of stars formed billions of years ago. Then, as it stretched into a stream, something extraordinary happened. Its scattered gas, thought to have been lost long ago, collapsed under its own gravity, igniting a surprise second act of star formation. Picture a phoenix, indeed a stellar population rising from its own ashes, defying the expectation that streams must be sterile relics. But where did the gas come from? That's where the plot thickens. Some researchers propose the stream plowed through a hidden cloud in the galactic halo, gathering enough material to spark new stars. Others suggest it retained gaseous tendrils during its disruption, threads too tenuous to detect until they suddenly coalesced. The wildest idea, that dark matter played a role, its invisible grip helping corral the gas long after the visible structure was torn apart. What makes Phoenix truly special is its rarity. Of the 60-plus stellar streams discovered in the Milky Way's halo, only one other, the young, metal-rich Jellum stream, shows similar signs of recent activity. This suggests we might be witnessing an entirely new class of object, streams that refuse to die, capable of stellar rebirth even as they unravel. The implications ripple through cosmology. If streams can form stars, they might contribute more to galactic growth than we ever imagined, their faint glow hiding engines of creation. Now the race is on to find more of these cosmic anomalies. Each new detection could rewrite our understanding of how galaxies cannibalize their neighbors, not just absorbing stars, but sometimes triggering new life in the process. The Phoenix stream, with its dual generations of stars, stands as a testament to the universe's relentless creativity. Even in destruction, it finds ways to build anew. Peering into the radiostatic of the Milky Way, astronomers uncovered something haunting: spiral arms that shouldn't exist. These phantom limbs stretch beyond the galaxy's classic four-armed structure, visible only as faint whispers in hydrogen emissions, completely absent from optical surveys where stars should trace their curves. It's as if our galaxy wears a second skeleton, invisible to the eye but palpable to radio telescopes, its ghostly extensions whispering secrets about forces shaping the Milky Way from the shadows. These dark arms aren't mere artifacts of fuzzy data. They're coherent, persistent structures first spotted in 21st-century hydrogen mapping projects like Thor and GasCap. While traditional spiral arms glitter with young stars and glowing nebulae, these specters are nearly starless, their presence betrayed only by the cold hydrogen gas weaving through them like cosmic cobwebs. Some, like the outer Scutum Centaurus arm, mirror the galaxy's known architecture but extend farther into the hinterlands, while others, like the faint Orion spur extensions, branch off at odd angles as if the Milky Way's spiral pattern frayed at the edges. What could create such star-deficient tendrils? One theory points to galactic collisions, ancient impacts with dwarf galaxies or dark matter clumps that sent ripples through the Milky Way's gas disk, leaving behind density waves where gas pooled but stars failed to form. Picture tossing a stone into a pond. The ripples persist long after the splash, even if no leaves float where they crest. Another idea suggests these arms are failed spiral features, regions where gas lacked the critical density to ignite star formation, leaving them frozen in potential. But the real puzzle is their motion. Spiral arms typically rotate with the galaxy, their patterns sustained by gravitational interactions. These ghost arms, however, seem to drift at different speeds, some lagging behind the galaxy's spin like celestial afterthoughts. That disconnect hints at external influences, perhaps tidal forces from the large Magellanic Cloud's gravitational tug, or even the lingering wake of the Gaia-Sausage merger, still warping the Milky Way's gas eons later. The most tantalizing clue lies in their magnetism. Recent polarization studies reveal these arms harbor unusually ordered magnetic fields, their lines weaving parallel to the gas filaments. This structure suggests the arms might be holding gas in place against disruptive forces, a cosmic loom where magnetic threads keep the fabric from unraveling. If true, it's a revelation. Magnetic fields may play a far greater role in galactic scaffolding than we ever imagined, quietly stitching together the universe's largest structures. What's unnerving is the implication that our galactic map is incomplete. If entire spiral features can hide in plain sight, what else might we be missing? These ghost arms could be the Milky Way's waypoints to a hidden history, one where collisions, dark matter, and magnetism conspire to shape galaxies in ways we're only beginning to trace. And somewhere in their radio whispers, there's a lesson. Sometimes the universe's loudest truths speak in frequencies we're only learning to hear. Deep in the galactic hinterlands, where stars fade into twilight, there lurks a celestial paradox, failed suns that somehow grew too heavy for their own destiny. Meet the overmassive brown dwarfs, cosmic misfits like SDSS J010, 4 + 1,535, that tip the scales at 90 times Jupiter's mass yet never summon the crushing heat needed to ignite fusion. These are not just failed stars, they're overachieving failures, challenging the very boundary between planet and star with their impossible heft. Brown dwarfs have long been the universe's middle children, too massive to be planets, yet too puny to shine like true stars. Most hover between 13 and 80 Jupiter masses, their cores too cool to fuse hydrogen but warm enough to glow faintly in infrared as they slowly cool into oblivion. But the overmassive outliers defy this tidy classification. How does an object accumulate enough gas to reach stellar proportions without ever crossing the threshold into stardom? It's like stacking kindling sky high yet never striking a match. One clue lies in their birthplaces. These heavyweight dwarfs often haunt dense star clusters or turbulent nebula regions where gas is plentiful but competition fierce. Picture a stellar nursery where collapsing gas clouds brawl for material. Some win and become stars, others lose and stall as planets. The overmassive dwarfs might be the rare in-betweens that gorged on gas just shy of ignition, their growth stunted not by scarcity but by timing. Perhaps they formed late when the surrounding disk had thinned, or in isolation where no shockwave triggered their final collapse. Yet even this explanation falters when faced with their chemistry. SDSS J010, 4 + 1,535, for instance, is a Methuselah among dwarfs, ancient, metal-poor, and bizarrely pristine, its atmosphere nearly devoid of elements heavier than helium. Such purity suggests it coalesced from primordial gas in the early universe, a relic from a time when the cosmic ingredient list was far simpler. But without metals to radiate away heat during formation, how did it avoid gathering enough mass to ignite? Simulations struggle to replicate such a scenario, leaving theorists to wonder if unknown physics like magnetic fields or turbulent braking might have capped its growth mid-collapse. The plot thickens when you consider their weather. Overmassive brown dwarfs are notorious for violent storms, their turbulent atmospheres swirling with molten iron and silicate clouds. On larger worlds, gravity would crush these tempests into submission, while true stars would vaporize them entirely. But in this Goldilocks zone of mass, the storms rage unchecked, their ferocity hinting at internal dynamics we're only beginning to fathom. Some researchers speculate these dwarfs might harbor layered interiors, where convection zones churn like malfunctioning engines, trapping heat that would otherwise fuel fusion. Perhaps the most tantalizing possibility is that these objects aren't failures at all, but rebels. By sheer chance, they may occupy a sweet spot where quantum effects in their degenerate cores stabilize them against collapse, creating a new class of hybrid object that thumb their noses at astrophysical norms. If so, the Milky Way could be riddled with these dark giants, invisible to most telescopes yet outnumbering stars in the galactic outskirts. What's certain is this: the overmassive brown dwarfs force us to redraw the line between star and planet, reminding us that nature doesn't care for our categories. They're cosmic riddles wrapped in cold, dim light, proof that even in failure, the universe finds ways to surprise us. And somewhere in their turbulent atmospheres, there might be clues to a deeper truth, that the boundary between star and planet was never as firm as we thought. At the very fringe of our galaxy, where the Milky Way starlight dissolves into the void, something bizarre waits: an invisible force field, a cosmic border patrol repelling intruders with a storm of high-energy particles. Voyager 1, humanity's farthest-flung emissary, stumbled upon this phenomenon in 2012 as it hurtled toward interstellar space. Just as the probe prepared to leave the sun's influence behind, its instruments screamed in alarm. Cosmic ray levels spiked to impossible levels, as if the spacecraft had slammed into an energy wall no one predicted. Scientists dubbed it the Galactic Barrier, and its existence forces us to confront a chilling question. What kind of force could corral an entire galaxy's worth of cosmic rays into a shimmering, lethal fence? The numbers alone boggle the mind. The barrier's cosmic ray density is 3 times higher than anything seen in interstellar space, a particle bombardment so intense it would fry unprotected electronics or DNA in moments. Yet the real puzzle isn't the intensity, it's the location. This energy fence sits roughly 120 astronomical units beyond the heliopause, the boundary where the solar wind gives way to the galactic medium. That puts it firmly within what should be a quiet transitional zone, not a particle gauntlet. If the Milky Way were a castle, this barrier isn't the outer wall. It's a moat filled with boiling oil, inexplicably placed halfway up the drawbridge. So what's generating this ferocious particle filter? One theory points to the galactic magnetic field, which grows stronger and more tangled near the Milky Way's edge. Picture the field lines as elastic bands stretched to their limit. As cosmic rays try to escape, the fields snap back, trapping and concentrating them like fish in a net. The trouble is, our current models can't explain why this effect would be so localized, creating a sharp boundary instead of a gradual incline. Another idea suggests the barrier might be a standing shock wave, a permanent sonic boom in the galactic wind. As the Milky Way plows through the sparse intergalactic medium, it could generate a bow shock, a ripple of compressed particles similar to the wake of a speedboat. Voyager, in this scenario, hit the equivalent of a cosmic wave crashing against the prow of our galactic ship. But here's the twist: some astronomers argue the barrier isn't a physical structure at all, but an illusion, a trick of perspective caused by the sun's own motion. As our solar system bobs up and down through the galactic plane, we might periodically punch into regions where interstellar magnetic fields align in a way that reflects cosmic rays back inward, creating the illusion of a wall. If true, the barrier would be less like a fence and more like a hall of mirrors, bending radiation into temporary traps that shift over millennia. Then there's the unsettling possibility that we're seeing the fingerprints of dark matter. Certain hypothetical particles, like weakly interacting massive particles, could accumulate at the galaxy's edge, their annihilation sparking the very particle storms Voyager detected. It's a long shot, but if proven, it would mean the barrier isn't just a curiosity, it's a shadowy sentinel, a border woven from the universe's most elusive substance. Whatever its origin, the galactic barrier forces us to rethink what it means to leave the Milky Way. Interstellar space might not be the serene ocean we imagined, but a labyrinth of invisible currents and deadly rapids. And as future probes like Voyager's successors push farther out, they'll test whether this barrier is a one-off anomaly or the first of many, a cosmic checkpoint reminding us that even in the void, no frontier comes without its guardians. From ghostly streams of resurrected stars to diamond-shrouded zombie suns, from black holes hurled into the void to galaxies hiding in our halo, we've journeyed through 30 of the Milky Way's most bewildering inhabitants. Each one defies expectation, forcing us to rewrite the cosmic rulebook. Think about what we've uncovered. A supermassive black hole that survives on cosmic crumbs, stellar graveyards where dead stars refuse to cool, and invisible walls patrolling our galaxy's edge like phantom sentinels. These aren't just curiosities, they're clues, revealing a Milky Way far stranger and more dynamic than we ever imagined. Consider the implications. The Great Attractor's invisible pull suggests entire swaths of the universe remain hidden from view. The Fermi Bubbles and Galactic geysers prove our galaxy's heart still crackles with violent energy. Overmassive brown dwarfs blur the line between star and planet, while dark spirals whisper of magnetic forces shaping the galaxy behind the scenes. Even the quietest corners hold surprises: stellar streams birthing new suns, ancient clouds waiting to ignite, and rogue black holes wandering unseen through the cosmic dark. What ties all these oddities together? A single, humbling truth: the universe thrives on exceptions. For every rule we've crafted: how stars form, how black holes behave, how galaxies evolve. The Milky Way presents an outlier that pushes the boundaries of possibility. And if our own backyard is this bizarre, what does that say about the cosmos beyond? This is just the beginning. For every mystery solved, a dozen more emerge. Could undiscovered black holes lurk in the galactic suburbs? Are there more phantom structures like the Radcliffe wave threading the spiral arms? Does dark matter weave through it all, its invisible fingers tugging at everything we see? The questions outnumber the answers, and that's the beauty of it. So stay curious, keep looking up, because the Milky Way isn't just a collection of stars. It's a living, breathing puzzle, its strangest pieces often hiding in plain sight. Who knows what we'll find next? Perhaps an even greater enigma is already out there, waiting for the right moment to reveal itself. Until then, let the wonder linger. The universe isn't done surprising us yet.